All right, so we're going to give you an overview basically of the atmosphere right now. We're going to talk a little bit about its origin, composition, structure, just kind of getting you a feel for what you're dealing with here. Uh, think about the atmosphere for a minute before we go on. The atmosphere actually is not very deep. Matter of fact, it's only about, maybe 10 to 20 miles up. So you think about that, and the part that actually controls the weather is even less than that. When we're talking about the atmosphere, we divide it into different sections and all. And there are different aspects that, the atmosphere covers the whole globe. So we're going to deal with things that come across. So here, for example, is a dust storm coming off the Saharas. This actually can have a major impact on tropical systems. When these dust storms come across and you see dust in the atmosphere, I have seen cases where San Juan, Puerto Rico, for example, will be down to a quarter-mile visibility, so they can't see very far, in dust. And it's all dust coming across the Atlantic Ocean from the Sahara Desert. And these dusts, actually do damage. Weather can go from very tranquil. I can sit out on the beach and have a great day out in the ocean. And the next day go out there and the wind's blowing, sand's blowing everywhere. The waves are very big and I'm not going out there. And you can actually see it can damage houses or it can be beautiful outside. You just want to spend the day out there with everybody. When we look at the Earth, we have a system, we call it an atmosphere, a hydrosphere, which is water, a geosphere, which is more the ground, the rocks, and then the biosphere is plant life, us. And here, example is an atmosphere is relatively thin. I was talking about that. It's composed of gases and suspended particles. There are particles of dust and other objects in the atmosphere. And believe it or not, half the mass of the atmosphere is within 18,000 feet. So, a little more than a 3-mile walk. So if you walk 3 miles, you've literally made it halfway through the atmosphere if you could do that in a vertical. And 99% of the mass is below 20 miles. You don't even have to run a marathon to get through 99% of the mass of the Earth and the atmosphere. So we're really talking a thin layer around the Earth. So in this thin layer, and we live in the homosphere, or this actually all the way down the troposphere, but it's made up mainly of nitrogen. The second most popular thing is oxygen, then argon, then CO2. CO2 fluctuates throughout the year, and it's gaining in percentage with time. Interestingly, if you climbed a mountain, for example, you would still have the same percentages. 20%, 21% oxygen, 78% nitrogen. However, gas gets thinner as it higher up it goes. There's less of it. So that 20% oxygen would make it really hard to breathe there because that's a lot less than if you're down here at the Earth. There are also water vapor and liquids in it. CO2 comes out, causes photosynthesis, and creates oxygen for us with time. And there can be man-made pollution, and there's also natural, like dust storms. Volcanoes give pollution, pollen. As the study of weather goes, we use the scientific method. I want to give you one quickie example of that. When I was working for the Weather Service, there's a real problem knowing when thunderstorms are going to move across the Appalachian Mountains. There will be times they come up to the Appalachians and die, and there'll be other times they come up to the Appalachians and just keep right on going. And since I'm on the east side of the Appalachians, I kind of like to make a good forecast for the people I serve. So we want to know why. So we came up with several hypotheses. One of the hypotheses was that how unstable the atmosphere is, and we're going to talk about that on the east side of the mountains, how that might impact these thunderstorms. So we started looking at that, and we were able to formulate a simple parameter that we decided to use and see and test. So we would test that against all these thunderstorms that have either come across or not come across and see how this parameter did. And we actually found we can set a certain value for that parameter, and the odds increased when the parameter went above that value that thunderstorms were going to keep coming east, and we were going to get hit with them. And when we were below that value, they went down. So as you can see, we used a scientific method to develop results that actually helped improve our forecasting. Here you can see the Purdue atmospheric model chamber. There are numerous mathematical models. I worked on them in college. I still, when I was working for the Weather Service, still played with some, just trying to improve our forecast. But one of the things, I'm going to show you a lot about the weather in this course. But know this, nobody in the mathematical field can solve the equations that govern the atmosphere. There just has never been that solution. So when we put that into a program and set up a program, it's always an approximation. Maybe a very good approximation sometimes, but it's always an approximation, which means every time you go out further and further in the weather, the more error is going to come into that. And some days error comes in real quick. Other days we might get a very good 10 to 14 day forecast. So that is an issue with numerical models. We have various observing systems. Here's ASOS. ASOS is at almost every airport in the country. It's at every major airport. Matter of fact, there may be a couple of them at some major airports. Why is that? The aircraft need to know what the conditions are before they take off and if they're landing. They need to know all the weather information. And then there are cooperative networks out there that provide literally daily weather, but they don't provide it in real time necessarily. They may have rain one day and we not see that how much they had until the next day. But we're getting better at getting that from them quicker. Radiosondes are just upper air balises of balloons. They carry a little instrument up, and every second as that instrument's going up, it's calculating a temperature, it's getting a pressure, and it's calculating the amount of moisture. So you wound up getting a vertical profile of the air. And here's a look at that little instrument. And it also, because of the way it moves, a radiosonde goes upwards, but that motion, we can calculate the wind as well. That's how it's moving. And when it's dropson, which they do out of an aircraft, this literally is the same type of instrument, except it's going downwards. So they calculate the same information, but it's dropping towards the center, maybe towards the center of a hurricane, for example. We have radars, which give you great information. That's one tool that we use all the time. Radars can provide you where the precipitation is. They can even measure where some clouds are sometimes. We have satellites that help that as well. And here you can see, notice the temperatures decrease in the troposphere. We live in the troposphere. Matter of fact, if you climb the highest mountain, you might barely make it into the stratosphere, but it would be very tough. So the troposphere is where we actually live, and that area temperature decreases with height. When you get above that in the stratosphere, notice it warms. Then we have another layer that decreases and another layer that warms. We basically use the transition in temperature to define the layer. The ionosphere is another part of the atmosphere. And with the solar wind increasing, we can get really neat auroras in the north and south poles. And you can see how they expand when that solar wind increases. So all of that to just say that will be what we're talking about moving through this semester. And here, for example, is a weather map. Again, just looking, say I was interested in just Ohio's weather, and I can zoom in very tight, and you'll see observations around Ohio here. You'll also see isobars drawn here. And you are going to be drawing some isobars on some weather maps in your e-investigations this week. One of the things to note here is there's the pressure, 134 millibars, or 125 millibars. Notice how it's gone down in that direction, 116 millibars. This line here, for example, is a value that's somewhere between this number and this number. The idea is to interpolate along here and find out where that line goes. And that's what you're going to be doing when you're drawing this week. You're going to discover where between 2 points a line might be. It's just connecting the dots, but you have got to supply the dots. So I hope you got a little bit out of this, and please let me know if you have any questions.